Hello, and thanks for joining me today. I'm here to talk about our work, which is towards latency-aware vNF placement on heterogeneous hosts at the network edge. This work is by myself and Professor Dimitris P. Pezaros from the University of Glasgow School of Computing Science. The paper has been accepted as a conference paper at the IEEE Global Communications Conference 2023. A quick introduction here. Software-defined networking basically allow service providers to separate control plane from the data plane of networking hardware devices. So typically you would have your router or firewall or load balancer, for example, and you're able to separate this control logic from the forwarding logic. That's the idea behind software-defined networking in general. That also brings in the concept of data plane programmability, where operators can define custom-built network functions. So NFV allows the creation of virtual network functions, which some examples are firewalls, load balancers, NAT, and etc. So we've also got the option to create a chain, which is a service function chain of these networks by network operators, of these vNFs by network operators, just so SLAs can be met based on the defined service level agreement. In terms of classification, we've got compute bound and IO bound vNFs. So some are basically computationally intensive more than the others. Relating NFV with edge computing, we see that there are a lot of use cases, modern use cases, but the environment itself, generally the edge environment is distributed in nature, and it connects to the public cloud, IoT network, enterprise network, home network as well. But the core is the internal NFV servers, where network operators have the option of deciding what hosts are there to host to place vNFs. So some edge use cases include smart grid e-healthcare mobile users, as well as autonomous vehicle, mixed reality, and industrial IoT. All these requests come from users, and network operators need to cater to these requests and place them efficiently on edge servers. NFV implementation, some of the frameworks that operators can use include SmartNICs or the Open vSwitch, Docker, for instance, for containerized functions, DPDK, eBPF. These are some of the options that are available to network operators when they want to place network functions at the edge. We've looked at some related work. First, Capio et al. Basically introduced hybrid placement on VMs and containers, and Moens et al. Did hardware and software functions placement. So that's the concept of hybrid placement generally. And Kawa et al. Introduced hybrid placements in environments where link utilization and bandwidth was the core metrics for evaluation. They used Shadajal et al. Also proposed a hybrid placement on edge cloud servers. So you start placing functions on the edge, and then you can use the cloud as well. Then Levadius et al. Did propose cloud edge placement as well, with the goal of minimizing end-to-end latency. The underlying architecture, the underlying capability of the hosts themselves is what we look at. So in terms of contribution, we investigate the optimal placement of vNFs over the distributed edge network while considering heterogeneity of underlying framework. So we do not assume that the frameworks are a flat list of functions with the same hosts with the same capability. So we look at that. How do they differ? We formulate and solve the hybrid vNF placement problem. This is as an integer linear programming problem first, then proposed hybrid placement heuristic that performs incremental placement. So what this does is rather than considering the global system parameters, we essentially look at a scenario where incremental placement can be carried out. The placement parameters, that's the model parameters. So I'll quickly run through this. So first, we've got the heterogeneous nodes, the physical network graph, that's G here. Links and node capacities, data plane, and user space host requirements. We've got user to vNF latency, supported link bandwidth, all the requirements such as the network functions to be placed as in components of the model, such as network functions to be placed, supported capacity of user space and data plane, link capacity, link latency, are all parts of the parameters we considered for the model. So first we started with two binary decision variables, X and Y. As you can see, that's equations 1 and 2. So binary decision variables 1 and 2. So data plane or user space placement, essentially. Then we made use of equation 3, which is the objective function that minimizes end-to-end latency. Then the capacity constraints are introduced in equation 4 and for 4a and 4b. Essentially, we're checking what's the capacity of the data plane nodes first before we carry out placements, and what's the capacity of user space nodes in equation 4b. In equation 5, what we're doing is we introduce a placement uniqueness constraint. So we're ensuring that functions are placed on the functions that have been placed on either user space or data plane packet processing elements are unique. And then we also look at link bandwidth constraint, equation 6, latency threshold, equation 7, and the path validity, equation 8, just to ensure that the path is valid at the time of placement. Link and latency, bandwidth and latency are essentially checking all the vNFs that you're trying to place if you've got enough bandwidth or latency to support those vNFs. The model you've seen so far requires a lot of computational time, which is not ideal, or I would say wouldn't fit in well for most edge network environments due to their dynamic nature. So we introduced this hybrid placement heuristic algorithm, which basically looks at incremental placements of network functions, and then it performs locally optimal placements on network functions on requests that are being sent in by users. So there is an assumption of network-wide information stability with the ILP, and then it's not ideal for large-scale deployments. The nature of edge networks are dynamic. That makes situations like latency fluctuations to cause downtime. So the heuristic algorithm is pretty straightforward because as you can see from the algorithm 1 here, it makes locally optimal decisions, incremental placement, which is near optimal, and then it prioritizes placements on data plane nodes. Then it's ideal for defining SLA for premium users. So because it's able to allow, it's able to reduce the number of latency violations, which we're going to see in subsequent slides. That makes it ideal for network operators that are trying to minimize the number of latency violations based on service level agreements. Then the idea of locally optimal decisions making as well makes it uh, uh, place network functions faster than the ILP model. So requests are being received, we check the data plane. If it's got capacity to host the functions, if it does, we take the function and update the requests, append it to the placement. If not, we use the user space nodes and we check the remaining requests and repeat the process until the requests are placed on functions. Then the latency and placements are returned. The evaluation environment we used, we made use of real-world topology, network topology, and the UK NREN backbone network. The solver, the optimization solver, we used is Eurobi. The persona latency measurements were used as well, the network X Python. This, the parameters link bandwidth, we did set that to a range between 100 to 1000. So this basically depends on what your infrastructure is able to support, what networks operators are able to do. And then the latency is sampled with this gamma distribution. So the latency measurements gotten from persona, the latency measurements, we sampled that using this distribution. Table 2 here is these some example use cases that you typically get with latencies ranging from 5 milliseconds to 80 milliseconds. Smart grids, mixed reality, service orchestration, monitoring applications as well. We started the evaluation by comparing two main scenarios. So that's user space only and hybrid. The last hop latency has been set to 2 milliseconds. So last hop latency here is the latency between the edge user and vNF it's trying to connect to. So we did set that to 2 milliseconds. 500 vNF placement requests were generated for this experiment, and then the lowest latency obtained was essentially in the hybrid scenario where you can see from the figure, the average user to vNF latency. This changes as the value of the number of vNF requests grow over time, and the data plane nodes are unable to host the requests that are being sent in by users. So the hybrid placement provides like a sweet spot because it's been able to cater to diverse vNF types. So because it's got a lot of resources, so it's able to host stateful and stateless functions, computational intensive functions, all kinds of functions can be placed on the user space. So much higher latency is obtained the user space only. Another evaluation we did carry out is to see the objective function, so the optimization and heuristic objective function. First, we did make use of 500 vNFs the requests. So that's for consistency with the previous experiments you've seen. So the capacity constraint is the key variable resources here, because that's what's happening when you, from what you're saying, hybrid placement 1 and hybrid placement 2, that's us varying, the capacity of the hybrid of the data plane or user space nodes. Data plane only essentially is got functions placed on data plane nodes. Then user space only functions on user space nodes. Then if you look at data plane only, that's 78% better than the user space only. Then the hybrid placement 1, what I just said now is we've got 50% of the functions placed on the data plane and 50 on 50%, the other half on user space nodes. That's 48% better than user space. Hybrid placement 2, we adjusted this so that 30% of the functions go to the data plane, just so we can see how this behaves in terms of the objective functions. And user space only essentially give the end-to-end latency, the highest end-to-end latency. So heuristic, which performs near optimal place objective function, is 20 times faster in terms of the speed of execution. You can see optimization and heuristic is pretty consistent across all the experiments we carried out. Another evaluation we did carry out was the number of placement requests that have been fulfilled. So if we are unable to place all network functions on the data plane due to its inability to cater to all types of functions, then we should be able to evaluate what number of placement requests are being fulfilled, because requests that are coming from users are pretty random, and we should be able to cater to that. So 500 vNF requests were generated for that as well. And we made use of a gamma distribution of k equal 1.6, theta is 0.5 for stateless functions. So these are functions that are lightweight. Your simple stateless firewall, for example, would fall into that category. And then we made use of k equal to 0.5 and theta equal 1 for stateful functions. So these are your essentially computationally intensive, compute intensive functions, stateful functions, maybe like a deep packet inspection module, for example, a DPI. And this distribution is what you're seeing in this figure. So that's it has a high occurrence of stateless vNFs, and then which suits real world characteristics of functions. So from the graph you're seeing below, which is a comparison of the number of fulfilled placement requests, above 80% of requests processed initially by the data plane, and that drops as the number of requests increases. So we attribute this to this distribution having fewer stateless functions as the number of requests grow, which makes it not suitable for the data plane to host. The final evaluation we carried out is the dynamic latency evaluation. So we basically made use of a time series because edge environments are not stable in terms of the users, the nature of users. So we could have mobile users moving, we could have path recalculation, a lot of things go on that would affect the latency over time. So we made use of 100 time series time instance. So an interval could be like 3 minutes. In an interval of 3 minutes in real world network, something could happen within that time frame. So we set that, and then latency threshold was set at 30 milliseconds. Note that network operators are able to set this threshold themselves, based on service level agreement by operators. So we observed that there are fewer latency violations with the heuristic algorithm, which is the green line, and then we got the highest latency violations with the optimization with the ILP model. So incremental placement by heuristic is attributed, we attribute that to this fewer latency violations we are seeing. Then we are able to see this difference because ILP considers global parameters when carrying out placements. So in conclusion, we've seen that there are lots of emerging edge computing use cases which require a new approach to in terms of being able to place these functions on edge devices, and then we can get improved performance by using data plane processing elements. So we can use that for vNF deployment since it essentially reduces the overheads in general. Hybrid placements can reduce chain-wide, that's SFC, service function chain packet processing delays, and then we can also delegate simple delay-sensitive operations. So for example, like a simple stateless firewall, for instance, can go to data plane elements, while we leave more complex stateful processing for user space functions like the packet inspection model, for instance. And then end-to-end programmability is achievable. That's if we're able to place functions on the data plane. Requests that come in, SFC requests that come in can have these functions placed on programmable data plane devices, which makes it flexible for network operators to define the functions. In terms of what we're looking at for the direction of this work, live vNF hybrid placement is one of them. That's rescheduling dynamically. We're already looking at this. Another direction is the in-band network telemetry and multi-domain service orchestration. Since we're trying to make use of these heterogeneous hosts to place network functions, there would be need to be able to orchestrate functions across multiple domains. Then intelligent hybrid edge placement is another area we hope to look at in terms of extending this work. I would like to thank you for your time, and please do send in any questions you've got to the email address provided, and I'll be glad to respond. Thank you.